This video shows calculations of the force of gravity between a person and various objects in our solar system. We're going to take a person with a mass of 72 kilograms and calculate the force of gravity to the Earth, to the Moon when you're looking at the full moon at midnight, the Sun in early January, Venus at the time of inferior conjunction when Venus is in between the Sun and the Earth, and Jupiter at opposition when Jupiter is opposite in the sky to the Sun. That's the time that Jupiter is closest to the Earth. We'll be using Newton's law of gravity. The force of gravity is the gravitational constant multiplied by the two masses and dividing by the square of the distance between the objects. And we'll be pretending that the person is a sphere, and the other mass that we're talking about is a sphere also. The constant of gravitation, this universal constant of gravitation, applies throughout the universe, 6.674 times 10 to the minus 11 in standard metric units, newtons times meters squared divided by kilograms squared. And we're not going to consider any orbital motions or any rotation of objects. We're just going to find the strength of gravity based on the masses involved and the distances involved. So let's go ahead and start this with the Earth. For the Earth, we have a mass of 5.972 times 10 to the 24th kilograms. And the person we're talking about is on the surface of the Earth. We're going to use an average size of the Earth, pretending the Earth is a sphere. So we have a radius 6.37 times 10 to the 6 meters. Now, do I have to correct this distance? This goes from the center of the Earth to the surface. Do I have to correct this distance in the calculation to get to the center of mass of the person? That would be roughly 1 meter above the ground. No, ignore 1 meter compared to 6.37 times 10 to the 6 meters. So you should pause the video and put these numbers in and do the calculation. The G we have, 72 kilograms. Mass 2 is mass of the Earth. Square the size of the Earth, the radius of the Earth, and divide that into your numerator. I came up with 707 newtons, 707 newtons. A quicker way to get the weight of a person, the force of gravity on a person, is to do m times g. And this is 72 times 9.81, and we get 706 newtons, essentially the same as 707. It's okay that those numbers are not exactly the same. They are close enough. So that was my check to make sure I did the capital G mm divided by r squared correctly. What about the moon? We're going to use the same formula. What changes here? Well, the constant of gravitation does not change. The person's mass does not change. But now we use the mass of the moon, 7.3477 times 10 to the 22nd kilograms. If you remember, the Earth is 10 to the 24th kilograms. And we're going to do a little calculation here for the distance between the center of the moon and the center of the person. The moon has an average distance from center of the moon to center of the Earth of 3.844 times 10 to the 8th meters. I am going to change the distance number we use in our calculation for gravity, accounting for the radius of the Earth, 6.37 times 10 to the 6. It's not a big effect on the change of the distance, but it is a change that takes place when we have an accounting for the Earth's radius. So the distance we're going to use in our calculations from the center of the moon to the center of the person, the distance average from Earth to moon goes to the center of moon, center of the Earth. So I'm subtracting off the Earth's radius, so we get center of the moon to the center of the person. Again, pause the video and put the numbers into the calculation. I came up with 2.47 times 10 to the minus 3 newtons. You may not be familiar with the effect of a newton of force, so if we change that to pounds with this conversion factor, multiplying by 1 pound for 4.45 newtons, the newtons units cancel, and we end up 5.55 times 10 to the minus 4 pounds. it is a small number. What about to the person and the sun in January? I picked January for a reason that to highlight another fact about the Earth and the sun. In the northern hemisphere, it is coldest in January. However, we are closest to the sun in January. It's the tilt of the Earth that changes the season. So I'm not going to get into that in this video. I've made other videos about that. So what do we use? Our mass 2 is now the mass of the sun. And notice 10 to the 30th kilograms. We've moved up from mass of the Earth of 10 to the 24th. Now we're in the 10 to the 30th realm of kilograms. We have a distance from the center of the sun to the center of the moon, 1.47 times 10 to the 11th meters at perihelion, when the Earth is closest to the sun. And should I subtract off the radius of the Earth? I don't need to bother. 10 to the 11th meters for the distance sun to Earth, 10 to the 6th meters for the radius of the Earth. It does not change my number noticeably, so I'm going to, in my calculation, continue to use 1.47 times 10 to the 11th meters. That will be close enough. Again, please do the calculation. I came up with 0.442 newtons, and again, converting to pounds, not insignificant, but it's small, 0.1 pounds. If you would do this in July, when the Earth is farthest from the sun, and we're hot in July because the Earth is tilted towards the sun in July, but at aphelion, it's not a great deal different. We're a little further away, 1.52 times 10 to the 11th meters at aphelion, so the force of gravity goes down a little bit, 0.413 newtons. Force of gravity between the Earth and between the sun and the person. And it's still, if you do the conversion, it's still about 0.1 pounds. All right, let's move to Venus. The Venus at the time of inferior conjunction, when Venus is in between the sun and the Earth, at that time, sort of an average value, again, we're dealing with elliptical orbits, so the number shifts around, but sort of an average distance at inferior conjunction is 4.1 times 10 to the 10th meters between the center of Venus and the center of the Earth. The mass of Venus has this value, 4.87 times 10 to the 24th. And again, the Earth's radius is not significant here. It's into the 10 to the 6th category for meters. Our distance to Venus, 10 to the 10th meters. So you can repeat this calculation if you want to with a better value for R, but I'm going to go ahead and use 4.1 times 10 to the 10th meters in calculating the force of gravity. Then I got 1.39 times 10 to the minus 5 newtons, again a very small number. What about Jupiter? Jupiter is our largest planet in the solar system, and let's do this calculation at the time of opposition. That's when Jupiter is in the opposite direction in the sky compared to the sun. The Earth is in between Jupiter and the sun. And we get mass of Jupiter here that I've looked up, and the opposition of 2022 was an especially close opposition, not dangerously close. We're still 10 to the 11th meters away, but this is as close as about as you get for considering the orbits of the two planets. And that distance was 5.9 times 10 to the 11 meters, again from center of Earth to center of Jupiter. Do I correct for the radius of the Earth? No. It's 10 to the 6th category, 10 to the 11th is our distance here. So I'm still going to use 5.9 times 10 to the 11th meters for the R value. And the force of gravity then between Jupiter and the person is 2.6 times 10 to the minus 5 newtons, another small number. Well, let's summarize what we have here. Force of gravitational attraction, and I'm not worrying about any orbit motion, any rotation motion in the planets of the Earth. I'm just strictly doing a calculation. What's the force of gravity given a mass, the two masses, and given the distance? So here's a summary. Hopefully it does not surprise you. The force of gravity on the person due to the Earth is far exceeding any of the other forces from objects in the solar system. only the sun, I chose not to put in the 4.42 times 10 to the minus 1. Only the sun did you really not need to use scientific notation to express the result. So I hope this helps you sleep well at night. The sun and the planets will not pull you away from the Earth. The force of gravity on you from the Earth is much stronger than the force of gravity from these other objects. Now, considering tides, there's a different formula for tides. Depends on r cubed. Not going to go into this video, but the sun and the moon are important for creating tides on the Earth. So, if you want to look at some more of my videos for physics and astronomy and some other topics that I've posted to YouTube, I have a list at my website, gpclements.com. This list is organized by topic, and for each video, there's the title of the video, a description of how many minutes the video lasts, a description of the content of the video, and for your convenience, a link, a direct link to YouTube, so you can click on that and view the video. You don't have to search at YouTube to find the videos. Everything here is free. You're not allowed to resell it, but it's all free, and you don't register. You don't give me your name or your email address or anything. And my website does not put cookies on your computer. That's a tech term that you don't need to worry about probably. Keep working problems, improve your comfort level in doing calculations, and ask your instructor if you have questions.